Great. Okay. So I forgot what I was saying. All right. Oh, okay. Yeah. Today we're covering more Numpy stuff. Okay. This is all taken from the Python Data Science Handbook by Jake Vanderplas. Great book. You should read it. Okay. So anyway, as always, import NumPy as NP. That's if you're going to use NumPy, right? And so again, with NumPy, you get the array. The array looks like a list, except you everything has to be of the same data type, and that speeds up calculations and operations very quickly in NumPy. And so highly recommend for any kind of data stuff. All right, so anyway, here I make two quick arrays. I'm going to go A range 4 and then A range 100, 104, and that produces 0, 1, 2, 3, 100, 101, 102, 103. Okay. And you can concatenate these together, all right? So there is np.concatenate. You give it a list or an iterable. This could be a tuple as well. Basically, you give it as the argument all the things that you want to concatenate. All right, so I put x and y into a list. So this is a list of arrays, and then it produces one array here. Okay. NP concatenate has an argument for the axis. The axes are 0 indexed. All right, and so I can say concatenate xy axis equal to 0, and it produces the exact same result that we had there. All right, no surprise there. Okay. All right, let's say we wanted to concatenate in the other direction, right? We got length 4 vector, and then, or length 4 array, and then I've got another length 4 array. What if I wanted to stack them on top of each other and make a 2 by 4 array? All right, we might say, well, let's try axis equal to 1. And what happens? We get an error. We get an error, right? Why do you think we're getting an error? Let me pull up the chat. Okay. The reason why we get an error is because axis 1 is out of bounds for an array of dimension 1. So if we look at the shape, right, how many dimensions this this array has, there's only one dimension, right? So there's a index 0 axis, but there's no index 1 axis. Okay. So if we wanted to do what we want, right, stack them on top of each other, we'd have to use something like vstack, okay? numpy.vstack, you give it a couple of arrays, and it's going to stack them vertically, right, which is, I think, what we wanted to do. Okay. What you can do, though, is you can take x and you can reshape it into a 1 by 4 array. All right, we reshape it into a 1 by 4, all right, and now I get this, okay? I reshape y, and now I have a two-dimensional vector, or two-dimensional array, right? It's two-dimensional, it's 1 by 4, and it's 1 by 4, but these are two-dimensional. We can tell it's two-dimensional because there's two opening square brackets here. And so here, if I do concatenate along axis 0, it concatenates along the 0 index axis, okay? Again, so 0 is for the rows and 1 is for the columns, right? So this is, if we look at the dimensions, what are the dimensions, or the shape, what's the shape of x? X is a 1 by 4 matrix, okay? It's got 1 row, 4 columns. This, the rows, is axis 0. And so when you concatenate along axis 0, it concatenates by row, okay? I can do concatenate along axis 1, and then it concatenates along the columns, okay? So it might feel a little strange that back here, when I concatenate them, it just goes along lengthwise. But that's because this is one-dimensional. So there's only one direction that you can concatenate, right? They're one-dimensional. So when you combine lines, right? If you're if you've got one line, a one-dimensional line and a one-dimensional line, there's only one way to extend lines, okay? You can't, there's no width to a line, so you can't stack them on top of each other. Now we've given it a dimension. We've given it a dimension here. We said there's rows and columns, and so I can concatenate row-wise, I can concatenate column-wise. Okay. All right, here I'm going to make two 2x3 matrices, right? So I do A range 6, 2x3, A range 100, 106, I guess by 1, this is unnecessary. But, and then we were going to reshape them into 2x3 matrices. Okay. So we ask what's the shape? They're both 2x3. Okay. So let's go ahead and we'll concatenate them. We concatenate by default, concatenates along axis 0. So it's going to concatenate row-wise. Right. But so if I don't specify the axis, it does it row-wise. I could specify the axis, right? I can specify axis equals 0, and I get the exact same result. I can also specify axis equals 1, and then it concatenates by column, and then I get what I expect also, right? So here I get a 4x3, and now I get a 2x6. Okay, and then you can always use VStack and HStack. Okay, so VStack and HStack, you don't have to. It's pretty much concatenate 0 or 1, but you know, for these two-dimensional things, right? Concatenate will work with higher dimensional arrays. So if you've got a 3-dimensional array, you can concatenate it this way, or this way. Okay, so with 3-dimensional arrays, you can do that, and 4-dimensional arrays, you can concatenate along any of those things, you know, assuming all the dimensions line up. Okay, math operators with NumPy arrays, right? So math operators in NumPy are vectorized. So, so we get high speed, high efficiency here, right? So you'd say take x 0, 1, 2, 3 and add 5, 5, 6, 7, 8. Okay. Add x and y 0, 1, 2, 3 with 100, 101, 102, 102, 103, and then it adds them, right? 100, 102, 104, 106. Element-wise addition. You can do element-wise multiplication. Okay. And you can take, you can call sum on the result here. Now we get 614. What is this equivalent to? What is this equivalent to as far as matrix operations or vector operations? Okay. So this is equivalent to the dot product of x and y. Okay. Dot product is you take each element and you multiply them by each element and you sum it up. Yeah, exactly. So you can also call np dot dot, and it does the exact same thing. It gives you back the same operator value. All right, here we've got two matrices. I've got the x matrix and the y matrix. X is, you know, 2 by 3, and y is also 2 by 3. All right, and so you can do +5, and 5 will get what we call broadcast. It's the similar concept as recycling in R, but in Python we call it broadcasting, or NumPy it's called broadcasting. Addition is element-wise addition. Multiplication, you can do the star operator is element-wise multiplication. You can also do np.multiply, and that will do element-wise multiplication. If you want to do matrix multiplication, you can call np.dot, right? And you know what? There is another matrix operator. I should include that in here. Okay. So here I can't do xm times ym directly, right? I have to take ym transpose. Okay. If I want to do a 2 by 3 by and multiply, it has to be multiplied by 3 by 2. So I would do a dot between xm and ym transpose, and I get this. You can also do xm dot ym transpose, and then there's one more. And this is a newer addition to, where did it go? there's one more that's equivalent. It's going to be xm at sign. At sign is the infix operator for matrix multiplication. Okay, so that can also be done. That will also work. Okay, so xm at sign ym, and this will give you infix style multiplication, matrix multiplication. All right, I'm going to just fly through this stuff because I think you already know. Okay, so I'm going to make a matrix or an array 0 through 3, 0, 1, 2, 3. We add 4, we subtract 5, we multiply by 2. Okay, everything does exactly what we did expect it to do. It applies the operation element-wise. Okay, we divide everything by 2. Notice over here, everything comes back as an integer. There's no decimal values. As soon as I do division, everything becomes a float. Yeah. Okay. You can take the negative of it. You can raise it to a power. This is how we do exponentiation in Python. We square everything. You can do modulo division. You can ask for absolute values. Okay. So, all right. You can do trig functions, okay? So trig functions don't exist in base Python. So you either have to load the math library, or you can load Numpy, and Numpy will have a ton of math operations. So as soon as you load Numpy, you can just do Numpy for any of these trig functions. Okay, so I'm going to do trig functions, and then I'm going to go from 0 to pi. So this is 0, 1/4 pi, 1/2 pi, 3/4 pi, and pi, okay? Or our floating point equivalents to those values, right? So linspace will do that, okay? So here, I can ask for sign of the vector theta, or the array theta, okay? And we get 0, this is the square root of 2 over 2, 1, root 2 over 2, and then this is pretty much 0 as well, right? Okay, cosine similar, 1, root 2 over 2, this is pretty much equal to 0, negative root 2 over 2, and negative 1. And then when you ask for tangent, okay, we get 0, 1, something approaching infinity, not quite, okay, but a very big number, all right, negative 1, and then pretty much 0 here, okay. Okay, there's log, okay, so you got the natural log, and then if you want log base 10, you call log 10, okay. So kind of as per tradition for statistics, whenever you see log, it's the natural log, log base e, okay. So you can ask, let's make y a range 3, which will go 0, 1, 2. And we can raise everything to the e, so you get 1 e, and this is e squared. You can also do raise 2 to powers. Okay, this is so this is going to be 1, 2. 2 squared is 4. Okay, and then there's also the power function. So you take whatever value you want raised to y. Okay, so 1, 3, 3 squared is 9, so on and so forth. Okay, so those are your math operators. I think we're kind of accustomed to seeing very similar operators in R. If you come from a R background, just note that they don't exist in base Python. You have to load one of the libraries, and in this case, it's the Numpy library. Right? I would say once you start using Numpy, you don't often load the math library as much because you know, you've already loaded Numpy, which pretty much contains a lot of the math library functions. Okay, I guess NumPy requires a little bit more overhead than math, but I don't think we care too much, right? All right. Sum is a function that exists in base Python, okay? And then there is NumPy's function, sum, okay? np.sum, right? If you go through the trouble of loading NumPy, you should use numpy.sum. Numpy.sum has been written and compiled. NumPy is basically this library that does Python and has a lot of optimized code running in C and things like that. But it's all made to make your life easier. You might as well use it. It's going to be better. NumPy.sum is way faster. Okay, so anyway, I have the numbers 0 through 99, and we say let's add all of these up, and you get 4950, right? So you guys learned the trick, right? You take each value, multiply by, divide by 2, right? So 99 times 100 divided by 2 gives us this, and there you go. So that's the sum. You can call numpy.sum, and for a one-dimensional array, the behaviors are exactly the same. Okay, no surprise here. But take a look at how fast this runs. Okay, so if you Jupyter, IPython specifically, and Jupyter uses IPython, has this magic function called time it, and you can give it a command, and it will time how long it takes to run that command. Okay, and it does it like 100 loops or 100,000 loops. It takes it and it measures how long it takes, and then it gives it calculates the standard deviation. So it taxes your computer. It took a while to run this. Okay, but notice how long it took to sum this. Okay, to sum this vector of 100 values. It takes on my computer about 2.29 milliseconds. Okay, that's not a lot of time. Okay, but 2.29 milliseconds plus or minus 508 microseconds per loop. Okay, so and then over here we have, but for the NumPy, it takes 9.3 microseconds plus or minus 301 nanoseconds. So this is on the order of 500 times faster. I don't know what this is. 2,000 divided by 9. Yeah, a lot. Yeah, maybe not 500. Maybe like 200 times faster. Okay, so NumPy has been coded in such a way to be very quick. So and sorry, this is a big array, meaning it's got it wasn't this thing with 100 numbers. It's got 10,000 random numbers here, 10,000 random uniform numbers, and to sum it up, it takes a different amount of time. Similar, you can search for the min and the max of these things. You can also search for the min and the max of these arrays. So this is an interesting statistical problem, right? If I take 10,000 random uniform values, what is, what's the expected value of your max? And what's the expected value of the min of 10,000 random uniform values? And you get something around here, okay? This is, but anyway, that's your min and that's your max. And you can time it, how long the min operator takes versus the NumPy min operator. And again, we're on the order of hundreds of times faster. 1.2 milliseconds versus 7.82 microseconds. Okay, time it will take a long time to run on your computer because it does thousands of these loops to get an accurate estimate. All right. The summary functions like min and the max and the NumPy or the sum values will behave differently for for two-dimensional structures or higher dimensional structures. Okay, so here I'm just shuffling these 12 integers. Okay, so so I take not 12 integers, yeah, 0 through 11. Okay, and then you can call random.shuffle, and it's going to shuffle the values inside the matrix or inside the array, and then we reshape the matrix to be 3 by 4. Okay, so here we go. And then if you call sum on the array, you're going to get column-wise sums. 11 plus 1 plus 2 gives us 14. 3, 6, and 9 adds up to 18. 4, 0, and 8 add up to 12. Okay, so regular old Python sum will add them up column-wise. Okay, NumPy will give you the sum of the entire matrix. Okay, NumPy will just say the sum of this matrix is 66. I think this is probably what we would expect. When I call sum on a matrix, I would expect it to just sum all the values in the matrix. You can get these values if you want. Okay, so here's my matrix. If you want the column-wise sums, what you do is you say, I want you to sum over axis 0. Okay, sum across axis 0. So 2, 1, 11 will add up to 14. 3, 6, 9 add up to 18. So you specify the axis that you wanted the sums to be performed over. Okay, here you can say sum over axis equal to 1. I want to sum it across the columns. Okay, 2 plus 3 plus 4 plus 10 adds up to 19. Each of these rows add up accordingly. Okay, so you can sum across the rows, sum across the columns by specifying the axis. Okay, similarly, the other operators like min and max will also work. Whoops, I might have put this matrix in the wrong spot here. So you can ask what's the min in each column. So find the min across rows. So the min of this first column is 1, the min of this second column is 3, the min of this column is 0, and the min of this column is 5. Okay, so you can specify np.min, and it will do that. Okay, here are two matrices, 2 by 3 matrices. And wait, I'm sorry, this shouldn't even be here. Okay, so you can ask, for this matrix, you can ask what is the standard deviation, okay? And then you can also say, I want the standard deviation across this axis and whatnot, okay? So this is, if you remember all of your apply functions in R, it's kind of like that, except you don't have to bother calling apply. You just say perform this summary function along this axis, okay? Which I think is quite nice, right? So any of these NumPy calculation functions will do that, right? Okay. Python and NumPy do not have a missing value character, okay? They have nan, okay? Nan is the float value for something that is not a number, okay? And this is kind of the stand-in for a missing value. One thing to note is that nan only exists as a float type. You don't have nan integers. Integers are not going to be nan, because nan, you know, the bitwise representation of nan is that I don't know, the integer bits are all maxed out, but the mantissa bits aren't all zeros. So, but anyway, so this is all, nan is always going to be a float type. Okay, so you can say x is going to be a float nan. This, you can directly create a nan value by just saying float on nan. Okay, and then when you say what is x, x will be nan. You say what's the type, and it will say it's a float value. Okay, and you know, certain calculations will result in nan. Like if you try to do infinity divided by infinity, infinity is technically a float value. It's not really infinity. It's just a numeric representation for something that basically, you know, there's the on the computer, the biggest number you can represent is on the order of 10 to the 308 power. So, you know, it's a big number, but it's far short of infinity. But if you try to represent something 10 to the 309 power, the computer's going to say, "Oh, that's too big. That's infinity." So anyway, this is what we got. These results result in nan. Okay. And if you try to add a nan to a number like 2, okay, it's going to come back and say that's not a number. So not a number added to a number is going to come back nan. Okay. There is a summary functions that are what we call nan aware. Okay. This is similar in R. Similar, you have the option for ignore missing values. Okay. You can have NumPy calculate nan aware sums, which mean basically just ignore the missing values. But this is a little bit risky, right? So it's kind of just like saying, I got 2 children. One of them is age 2, and then the other is, I forgot how old my other kid is. And then you say, all right, what's the combined ages of my children? The true answer is, well, we don't know because you don't know how old your other kid is, okay? But here we're just saying, oh, well, the combined ages of the children, ages that you do know, well, that's 2, okay? And notice that because this is, this comes in as an integer, but because x is a float, which is nan is a float, this is gonna get upcast to become a float. So our result is going to be a float 2.0, right? And we can always, Python's very good in that it will let you know that this is integer because there's no dots, and then we'll let you know this is a float because there is a decimal place. Okay, so these are pretty much all of the summary functions, and then these are the nan-safe versions, right? So you've got sum, product, mean, standard deviation, variance, min, max, argmin, argmax, all of that stuff, right? Okay. There's no nan-aware things for these Boolean things of any or all. Okay. All right, let me talk about broadcasting. Okay. So first I create these 2 arrays, 1, 2, 3, and 4, 5, 6, and here I'm just adding them together. We've already seen this behavior. Okay. If you try to add, say, here if we create a vector or an array with length 2, okay, this will not let you do it. Okay. R does funny recycling, right? It would add the 7 to the 1, the 8 to the 2, and then add a 7 back to the 3. Okay. That's what R does. R recycles and it says, oh, I reached the end and I did it. It gives you a warning and says, you know, I didn't use the 8, and so, you know, but when you do it for Python, it says, hey, you gave me one array where the dimension is 3 and another array where the dimension is 2. You can't do that, right? It says operands can't be broadcast together. Okay, so let me just show you what broadcasting does. All right, so A is this array, 1, 2, 3. E is a 3 by 3 array, okay? It's got a bunch of 1s in there, okay? If I add E and A, what happens? Okay, this 1, 2, 3 gets added to the first row, and 1, 2, 3 gets added to the second row, gets added to the third row, okay? It's basically what it's doing is it's going to broadcast this row into another matrix of 1, 2, 3, 1, 2, 3, 1, 2, 3, and then it adds the matrix of 1s with the matrix of 1, 2, 3, 1, 2, 3, 1, 2, 3 together to give me this. All right. If you want it to go column-wise, then we have to reshape A like this, okay? And it's going to go, you get a column, 1, 2, 3, right? If I reshape it this way, and I add it to E, then it will get broadcast, okay? this 1, 2, 3 will get broadcast into a matrix that goes 1, 2, 3 down one column, 1, 2, 3 down the next column, 1, 2, 3 down the next column, so that the shape of this thing matches the shape of this thing, and we can add it. Oh, quiz answers. Man, I forgot what my quiz answers were. What did I make for today's quiz? I guess you will see the answers. Okay, it's E and A. Today's quiz answers are E and A. Those are the quiz answers for today. Okay, you guys got that? E and A. All right, so so we broadcast this down the columns, and we get this. All right. So what Python NumPy is doing internally is it's taking this, and it's going to basically duplicate it across columns so that you get another matrix that's also 3 by 3, and it combines the two. Okay. So you can do this with other stuff, right? So here, I've got this 2 by 3 matrix or 2 by 3 array, and here I've got a one-dimensional array, and I can broadcast it. This is not a 1 by 3 array. It's a one-dimensional length 3 array, right? There's a difference there, right? So this is basically a vector. It's a one-dimensional length 3 array, but you can broadcast it no problem here. Okay, D plus A is going to broadcast. It's going to kind of V-stack these to get basically another 2 by 3, and it adds them together. Okay, here is C, and here is D. Okay, and when you try to do this, okay, Python gets upset, right? It says, hey, this thing, D, is 2 by 3, okay? And then this other thing is a length 2. It's a length 2, and Python isn't comfortable with transposing it on its own, okay? So it just says, hey, I can't do that, all right? So what we have to do is we have to reshape this to be a 2 by 1, okay? And then it will broadcast, and then it will go 7 will get added to the 1, 8 gets added to the 4, 7 gets added to the 2 to make 9, 8 gets added to the 5 to get 13, okay? See, we have to reshape it basically into a column. 2 rows, 1 column here. Okay, here's the kind of the most impressive broadcast. Okay, here I have a column matrix at 10 by 1, and here I have a 1 by actually this is just a one-dimensional basically row vector. Okay, this is a length, or this is technically a length 11 vector, and here I've got a 10 by 1 thing. Okay, you can actually add these together or multiply these together, and Python will broadcast them. Okay, what it's going to do is it's going to say, hey, this is length 11, this thing is 10 by 1, and it's going to broadcast them into compatible dimensions and then add them together. So it's going to duplicate these columns so that there will be 11 of them, and it's going to duplicate this so that there's going to be 10 rows. And then, so it broadcasts this into a 10 by 11 matrix, and it will broadcast this into a 10 by 11 matrix. Right, and it will work. Okay, do the order in which you add matter. You know, for this, here I'll show you. So let's. Okay, so I got this, and then okay, so we wanted. Oops. All right, so we've done print E plus F. Let's do print F plus E. Okay, and we get the same results. Okay, so F is kind of the row, and E is the column. And so basically, what Python will do is it looks at the dimensions of F, it looks at the dimensions of E, and it.
Sorry, I'm not sure about that.
Sorry, I guess Alexa's listening in on me. F and E or E and F will it will look at the dimensions and broadcast them accordingly. Okay. All right. So you can do element-wise multiplication, and basically we get the times table. Okay. And here you can take D and you can you can try to reshape them into 1 by 6s and 6 by 1, and then it will also it will broadcast, right? So these things work that way. Okay. Oh, all right. Let me keep going. Boolean operators. Okay. So the Boolean operators in Numpy work different from the Boolean operators in base Python. Okay. And what it's so in base Python, you have things like true or false and those operators, and you use those words and you generally put them in if statements. Okay. When you're doing Boolean operators in Numpy, you're dealing with arrays, and so you will get kind of array answers. All right. So don't mix up the Boolean operators that we use for Numpy with kind of the Boolean operators that go inside of if statements to kind of control the flow of your programming. All right, so here I just created a vector, and then I can just say is x less than 3, and then we get the vectorized results, true, 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 false, 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 exactly as I expect. X greater than or equal to 3 will give me basically the complement. X equal to 3 gives me exactly what I expect. Okay, you can use that. You can use an array with Boolean values to subset in Python, much like we would do in R. So we can say subset X, okay, using square bracket notation, and we give it this Boolean array. Okay, this is something that really only Numpy supports. Okay, all right. You can say I want to sum the values that are greater than 3, right? And so what this is going to do is it's going to upcast the logical values into 1 and 0 integers, okay? And so you'll get how many values are 3. Similarly, if you call mean, it's going to upcast them to 1s and 0s and find out the proportion, okay? And then, and this is something you got to get used to. Don't use the exclamation point for negation. You use the tilde, okay? Tilde means not, okay? So not x equal 3 will give you this. So this is just different symbols, but this is the negation. So false becomes true and true become false. Okay, and you can do similar stuff with a matrix. So here's a matrix, and you can say which of these are greater than or equal to 6, and those ones are 6 through 11. You can add how many are greater than 6, and you can do you can sum across the this resulting Boolean matrix, okay, provided like with axis 0, and it will tell you how many values in each column are greater than 6. So we get 1, 1, 2, 2. Or across the rows and things like that. Okay, so inside, when you have these arrays, true, true, false, false, true, false, true, false, okay, the ampersand, okay, ampersand is what we call bitwise and, okay. This, whereas Python you have the and operator, okay. So you have bitwise and, bitwise or, and bitwise exclusive or, okay. Exclusive or means one has to be true and one has to be false for it to return true, okay. So these are the bitwise operators, which are different from the word spelled out AND and the word spelled out OR. we've already seen the negation operator for bitwise not, okay? And then you've got true, any and all, which will check to see if any of the values are true or if all the values inside the array are true or false. All right. Regular lists don't support fancy indexing, but NumPy does. What's fancy indexing? That allows you to select values in some kind of array by specifying I want index 0, index 1, and index 5. So index 0 is 37, index 1 is 12, and index 5 is, in this case, 5, coincidentally. Okay, and you can do something similar here, okay? So here I've got this matrix, and this represents indices, okay? So here it says I want index 1, index 4, index 7, okay? And we're going to subset X, okay, which again is just an array, and we're going to pull index 1, index 4, and index 7. And the results get arranged into a matrix. Right? So that's kind of neat, right? So we're subsetting a one-dimensional array using a two-dimensional index, and the result's going to be this two-dimensional array. Okay, here is a new matrix, a new two-dimensional array, 3 rows, 4 columns. Okay, and you can also give it basically coordinates. Right? I want row 0, column 2. Okay, row 0, column 2 is going to give us 2. I want row 1, column 1. Okay, row 1, column 1. Again, it's 0 indexed, so row 1 is this row. Column 1 is this column, so it gives us back 5. Row index 2, column index 3. That's going to be the last value there, 11. So that's what we got there. Okay, you can do sorting with NumPy things. Okay, so here I shuffled the values in X, and we get this. We can sort them, and it does exactly what we would expect. All right. So keep in mind when you call sort on X, it sorts it in place, right? So X gets sorted in place, even if I didn't print it out. So this doesn't print any thing out. Okay. You got to print it out to see the result. Okay. Here's Y. Y is 5214, and then we can call argsort. Okay, argsort gives the index of the values to have proper sorting. So it's going to say if you want to sort the values in Y, you're going to choose index 2, which is 1, then index 1, which is 2, then index 3, which is 4, and then index 0, which is 5, if we want these in order. Okay, and so if you say, okay, Y is the result of argsort, and then you subset Y using argsort, then you'll get the values in sorted order. Okay, you can also apply sorts along particular axes. All right, so here I can say sort across axis 0. So here I've got all these shuffled values. Okay, and then when I say sort along axis 0, it's going to sort column 1, 1, 5, 5, 7. It sorts column this column index 0. The next column, it sorts in order from least to greatest. It basically just takes each column of values and sorts them. Okay, you can also do it across rows, and it's going to do exactly what we expect it to be. Okay, last page. All right, so if you want to subset a row out of a matrix, okay, you say, you give it the row, and then you don't leave it blank, but you put in a colon to say I want all of the values in that row. Or again, you can call argsort. Basically, the results of each of these things are arrays themselves, and so here we can say argsort X, this column 1, and it says, okay, if you want to put these in order, you go index 2, then index 1, which is 7, then index 0, which is 8, and then index 3, which is 9. And that will give you the results, 2, 7, 8, 9. Okay. All right, and so what is this doing? Okay, here I'm subsetting X using argsort on the first index 1 column, and then we're selecting all the columns. Okay, so how am I subsetting this? Basically, what I'm doing is I am arranging this matrix. I am arranging the matrix by the in order of the second column. So I'm going, I want the second, or I want this index 1 column, okay, 2, 7, 8, 9. I want it in that order and rearrange the rows accordingly, okay? Which is different from just calling sort on the axis 0, because it sorts each column independent of each other. But here it's kind of like if you have, if you want to sort based on a particular column, this is one way to do it. All right, I hope that makes sense. That's all I've got for you guys today. On Friday, we'll resume in the Think Python textbook. We took a side detour to talk about NumPy, and then on Friday we'll resume Think Python. We'll look at files and all sorts of stuff, and I'll work on another homework assignment for you guys. How's this homework coming along?